Hi, I'm Jongkyu Park. I graduated from Sungkyungan University under the guidance of Professor Young Igam. This work has been published at PPOP this year. PPOP is a top-tier conference focusing on parallel computing. This paper addresses a conventional approach to handling race conditions, which is log. In detail, I will discuss how we integrate scheduling capability with logs. Logs are typically not considered as a resource that requires fair scheduling. However, we argue that similar to other resources like CPU and I/O, having a log scheduler can solve various real-world problems, including performance interference among containers or applications. And to solve this problem, we propose a new log design that provides proportional log sharing. Data centers typically have a low resource utilization because they always have to be ready to serve random demand spikes. So modern data centers oftentimes co-locate different applications into the same machine to increase resource utilization. For example, we can co-locate latency-sensitive applications and batch applications in a single machine using virtualization technology. Similarly, microservices from a single user in the public cloud setting oftentimes are encapsulated by container and locate in the same virtual machine. But the problem is, in this case, they share the underlying system resources, which can incur performance interference among such instances. To prevent this, Linux utilizes cgroup to manage hardware resource in a unit of container and provide performance isolation among them. In specific, each resource is managed by a dedicated scheduler which cooperates with cgroup, which is Linux resource management technology. For example, CPU resource is managed by CFS, which utilize virtual runtime and red-black tree. It tries to fairly distribute CPU time considering application or process or thread priorities by picking the threads with the lowest vRun time for the next entity to occupy that particular core. Similarly, storage I/O is managed by I/O schedulers such as BFQ. In the case of BFQ, it tries to distribute I/O bandwidth to applications considering their priorities. Both scheduler work with cgroup in the case of cgroup scheduling, like container environments. However, we currently do not have a fair log scheduler for proportionally distributing log resource to applications or containers. Logs are similar to other physical resources like CPUs or IOs, block IOs, in that they suspend application executions. For example, when a thread couldn't acquire the lock but tries to acquire the lock, it should wait for the lock holder to release the lock. Until then, it cannot proceed its task. Therefore, the lock management sometimes significantly affects application performance, and its wrong management can incur various problems, including performance interference. This problem becomes more serious when application characteristics are different. Suppose there are 3 different threads from different applications where their priority and critical section length are different. Thread A is from, suppose the thread A is from one application, and thread B and C are from the same application. And they all compete for a particular FIFO base lock. Here first, the thread A acquires the lock and performs its operations in its critical section. Here, critical section means the period during a particular thread acquires the lock and releases the lock. And then, thread B acquires a lock and performs its job within its critical section. Here, the critical section size of B is larger than that of A, and this phenomenon can happen commonly in real world because each thread can perform different operations within their critical sections, and even if they do the same job within the critical section, depending on the data structure size, the critical section lengths can be different. And then thread C does the same. Here, thread C has the longest critical section. In this case, although the number of lock acquisition is the same across threads, thread C held the lock longer than the others. From application's perspective, application of thread A received much lower lock resource than the others, especially since thread A has twice higher priority than others. Since priority of A is 200 and the priority value of B is 100, we can say lock resource is not fairly and proportionally distributed. To measure the consequence of unfair lock occupation, we run a file server while running a batch workload that repetitively performs renaming tasks. In this scenario, they are encapsulated in individual container and C group so that we can say they are isolated. They both try to acquire the system-wide rename lock, which applications require when they are performing rename task. Here, since file server is a performance critical application, we set its priority higher than the batch workload. This figure shows the file server throughput is in a time series manner, while we vary the number of threads in the batch workload. Here we use the default Linux spin lock for the rename lock. As we increase the number of threads in the batch workload, the performance of file server gradually decreases because the rename lock becomes more contended. This means the behavior of a single container or application can affect the others in the same system, although they are isolated by C group and container, which means performance interference. This leg of proportional lock management can incur various problems. First, as we just see, the behavior of a particular container or application can affect the others, even though they are isolated by C group or container technology. Second, since application priority is not reflected in the lock management, high priority one can be oftentimes suspended by low priority one with long critical section, which is called priority inversion. Finally, a few threads with very long critical section can degrade the entire system performance since other threads should wait without doing their tasks. To overcome such a problem, we suggest that 4 requirements should be met. First, regardless of critical section size and the frequency of lock acquisition request, the lock should be able to provide fair lock resource distribution. Second, to integrate with the modern scheduling API, locks should be able to support proportional resource sharing and C-group integration. This means we argue that if a thread has twice higher priority than the other, that thread should occupy twice larger amount of lock than the other instead of considering only the number of lock acquisition. From performance perspective, the lock should be always occupied, if possible, without keeping the lock idle when there are lock waiters. Finally, the underlying architecture like NUMA should be considered for the sake of high performance and scalability. To provide proportional lock sharing, we designed a new lock primitive called CFL. Basically, what we are trying to do here is to apply proportional scheduling to the existing queued lock by learning the conventional wisdom from CFS and BFQ. For scheduling policy, we adopt 2 metrics. First, we keep track of virtual lock hold time, which is the amount of lock occupation time considering application priority per thread and its average value for the entire lock waiting queue. Second, we also calculate per socket average virtual lock hold time and the minimum socket ID, whose virtual lock hold time is the lowest. So we maintain this value to provide NUMA awareness. There are 2 conditions where CFL prioritized thread in the lock management. First, virtual lock hold time of a particular thread should be lower than the average virtual lock hold time of the entire lock waiting queue. And also the second one is it should locate on the minimum socket ID. For scheduling mechanism, we dedicate one particular thread as a lock scheduler at a time, and it traverses the queue to reorder the queue, which performs as scheduling and collecting the virtual lock hold time information of the current lock waiting queue. We additionally perform reverse traverse. That's why we adopt doubly linked list instead of using singly linked list to further collect virtual lock hold time information of threads that are ahead of the lock scheduler. So for example here, since T3 is the lock scheduler, by performing reverse traversing, we can collect the virtual lock hold time information of T1 and T2. I will briefly explain CFL using an example. First, the average virtual lock hold time and mean SID are located in the lock structure, and per thread queue node includes the per thread virtual lock hold time and its socket ID. First, when a new thread tries to hold the lock that are already occupied, then it is added to the tail of the queue, which is the basic queued lock behavior. And then the lock scheduler thread here, T3, traverses the queue and collects the virtual lock hold time information. When it encounters any thread that meets the criteria that I just explained, it reorders the queue so that the thread locates right behind the lock scheduler. Here T6 was at the tail before, but now it has moved to the front side. After that, lock scheduler performs reverse traverse to collect virtual lock hold time information ahead of the lock scheduler, since they are not accessed during the normal traversing process. Finally, it updates the average lock hold time variable and transfers the lock scheduler authority to the lastly moved thread, which is T6 here. When the lock holder thread releases the lock, the head of the queue will carry the lock. The reordering process moves threads that have relatively lower virtual lock hold time to the front side so that it can prioritize such thread. By repetitively performing this process, CFL can make virtual lock hold time of all the threads similar to each other, which means fair lock occupation, other than equalizing the number of lock acquisition. And the virtual lock hold time slowly increases as the priority increases. High priority ones will be likely to occupy the lock for a larger amount than the others. There are a bunch of optimizations for both performance and fairness. To support group scheduling, we additionally add cgroup ID and collectively manage threads within the same cgroup and use them to manage resource in a unit of cgroup. For the other optimizations, please refer to the paper. We ran the same evaluation as the motivational one with various locks, including syncord, which is very similar to what we do, and NUMA-aware locks. This figure shows the file server throughput in a time series manner, and we start the batch workload at the start mark. As the batch workload begins to run, the throughput of file server decreases because of the contention for the rename lock, and other locks cannot reflect the application priority due to lack of fair lock scheduling. In the case of syncord, it cannot support group scheduling. It gives more lock resource to the lower priority ones. However, CFL, which is our approach, fairly schedules lock resources in a unit of cgroup and boosts the performance of file server since it has higher priority than the other. As a result, CFL shows higher performance than others by up to around 7.1 times. And when it comes to average latency, CFL decreases the latency by around 57% compared with the default Linux spin lock. We also tested our lock with RocksDB. In the case of RocksDB, the foreground tasks and background tasks compete for the several locks related to the page cache, which is a cache space residing in the main memory inside the Linux kernel. Here, foreground tasks means the thread that processes user requests, while background ones perform other tasks such as compaction. We enabled performance optimization options supported by the default RocksDB that gives higher priority to foreground tasks to improve user perceivable performance. In the case of other locks, they do not have ability to prioritize particular thread in the lock management, so they cannot distinguish and prioritize foreground threads, although the option is enabled. On the other hand, CFL prioritizes foreground threads in the process of lock management. As a result, CFL can outperform other locks by up to 1.86 times, mainly due to its ability to preferentially give more lock resources to the foreground tasks, which is directly communicating with the users. In conclusion, lack of proportional lock scheduler can incur various problems, including performance interference. And to overcome these problems, we design a new lock primitive that includes proportional lock scheduling. CFL, our approach, supports C-group integration and various other performance optimizations that I didn't talk in this talk. We also implemented CFL both inside the Linux kernel and at the application layer. Please refer to the paper for further details, and thanks for listening.